Right. I hope everyone is good. So today, before we're going to discuss chemical kinetics. One of the topics in chemistry that's so close to my heart. So the objectives to further we're going to discuss the definition of reaction rates. To further we're going to discuss my factors. I'm going to affect the rates of chemical reactions. And we're also trying to discuss how we measure Maret's chemical reactions. Just three things for today. Okay, now, what do we mean by chemical kinetics? So, tiambigai with the word kinetics itself. So, kinetics is of or relating to speed. Not speed as in I show speed, but speed. So chili Jones say to do with speed, kinetics, right? Speed, motion, just anything to do with movement, kinetics. Ku physics mutakore munavanga what you call kinematics. A slightly similar concept, but fundamentally different. Kinematics or physics, which you say you study motion without considering the cause of the motion, right? Anyways, that's a discussion for a separate playlist. But kinetics of or relating to speed, anything to do with speed, motion, kinetics, right? So chemical kinetics, the branch of chemistry or the area of chemistry that is concerned with the speed kapena kuti ma rates at which my chemical reaction amachitikira, right? So in chemical kinetics, the fundamental question we're asking in chemical kinetics, the fundamental question we're asking is how fast is a chemical reaction going, right? So how fast is a chemical reaction taking place? That is the whole essence of chemical kinetics. What we're interested in the whole chemical reaction is just how fast is that chemical reaction taking place. So you might wonder, like, why do we care? How fast a chemical reaction is taking place? There are so many implications. I'll go into detail later, but for now, think about food decay. That's a chemical reaction. You want to know how fast does this chemical reaction take place? How soon does my mango, my apple, my bread go bad? Because if you know that, then you can be able to design my preservative. Or then I would, okay, if my mango imabanga go bad in 5 days, then I need a preservative. Imenenga inga bangese whether my mango should stay longer than 5 days. Because if you don't know whether your mango goes bad after how long, then you're blind. You can't essentially design a proper preservative, right? So I'll go into detail later, as into why we care as to how fast a chemical reaction is taking place or not. So that's the whole essence of chemical kinetics. How fast is a chemical reaction taking place, right? Now, a very, very important aspect of the whole subject of chemical kinetics is the reaction rate. The reaction rate. So the reaction rate, or just the rate as we'll be calling it, we'll just be calling it the rate for simplicity, is the change in the concentration of reactant or product with time, just as it is. So what do I mean? For the sake of notation, concentration agent, we use square brackets. For example, we say the concentration of A. concentration of B, the concentration of reactants, the concentration of products. So the square brackets, you read them as the concentration of whatever is inside them, the concentration of whatever is inside them, the concentration of reactants, the concentration of products, right? So the change in the concentration of a reactant or a product with time is called the reaction rate. So we can say the rate equals the change, delta means change, delta means final minus initial of a certain quantity. So in this case, the quantity is the concentration of products over the change in time. What this essentially means is the concentration of products, final, F for final, minus the concentration of products, I for initial, over time final minus time initial. That's what it means. Now, my products are being formed, right? My products are being formed. Therefore, the final concentration, this one, will be higher than the initial concentration for products, right? So let me write that on a separate space. We're saying the concentration of products final is greater than the concentration of products initial. Therefore, the final concentration minus the initial concentration, it was a positive number. The numerator will be positive because this is larger than that. At the same time, ntawi imangubira kutsogolo, so the final time will be larger than the initial time. So the final time minus the initial time will also give us a positive number. A positive number divided by a positive number will give us a positive number. And conventionally, my scientists anagwiriza kuti rate should always be reported as a positive number. So as this definition is correct and does not need any modification, as opposed to if we are defining the rate in terms of the concentration of reactants. Okay, so if we are defining the rate in terms of the concentration of reactants, then we need to put a negative sign in front. And the reason for that is the final reactant concentration minus the initial reactants concentration will give us a negative number because reactants are being consumed. My reactants are water, therefore wayamba nane bwambiri kumabeetu alipo ochepa less. So less minus more gives us a negative number, right? This is the numerator only. Amene pansipa pali bwinobwino. Time final minus time initial is still positive. So you do know that negative divided by positive, answer like yani negative. But then we need this whole thing to be positive. A simple trick would simply be to multiply the whole thing by negative. So that negative and this negative make a positive, and this positive divided by this positive give us a positive for the rate as we require it to be. that's all about the rate of a reaction. You can define it in terms of the change in the concentration of reactants or in terms of the change in the concentration of products. So once again, we're saying the reaction rate is the negative of the change in the reactant's concentration over time, or the positive of the change in the concentration of products with respect to time. I hope by now you understand why we need this negative sign in front. Perfect. Now, one more thing. Let me remove this bit. Okay, products. Now, units of reaction rate. It's very important to note that pamwamba my units ake akala molar or capital M, molar, just M, or mole per liter. All of these three things are the same: molar or capital M or mole per liter. Right? Pasiba, my units are seconds. Now, that being the case, it means we can have molar per second, right? Or we can have mole per liter per second. I mean, so you can write it better as mole per liter multiplied by second. My brackets or taguiga or wasaiga is still the same, right? Or if you want to get more fancy, let me write this here. So you could say mole per liter per second, or mole multiplied by liter to the minus 1 multiplied by second to the minus 1. Simply because liter to the minus 1, the 1 over liter, second to the minus 1, the 1 over second. Perfect. So these three are the same. You can write molar per second, you can write mole per liter per second, or you can write mole per liter per second, omega yonch. All of these are units of reaction rates. Okay, now just a point to note: any chemical reaction can be written in the general form. Reactants to products. Just for the sake of the discussion we're going to have next, just keep in mind that we can write any chemical equation in this general form as long as it is an irreversible reaction, not reversible. Reversible, in a kind of forward and reverse reaction. Reverse reactions. Irreversible only has the forward reaction. So if your reaction is of that form, then you can simply say reactants to products. So we're going to stop here for today, and next we'll continue with the factors that affect the rates of chemical reactions. Until next time, stay blessed.